So everybody can write this down. Put it in your journals that we started class on time today. Okay. So it happens every once in a while. Does anybody have any questions from the homework they'd like to take a look at? On the homework? Which, so going towards the second homework, this one? Number 19. This might have been one we looked at yesterday. No, I'm going to push it back.
Are you pushing it to the next test?
Yeah. It'll get pushed back to the next test. So this is going to be a counting problem. And what we're going to do today is we're going to also see some examples where we can use counting strategies for probabilities. So this says that the appeal process, it requires the jury to be selected from 5 individuals, from 9 students and 11 faculty. So what's the probability of selecting a jury of all students, and what is the probability of selecting a jury of all faculty? And what's the probability of selecting a jury of 3 students and 2 faculty? Yeah? There's actually, there's multiple ways to tackle A and B. So, but C requires something a little more difficult. So, we'll look at that. Maybe, I'm trying to decide if I want to. Well, we can just look at it. It'll be fine. So let's do some blank documents or something here. So let's see here. What was the setup here? What was the numbers? In mine in particular, it was we needed 5 people, 9 students, 11 faculty. 5, 9, and 11. So it's 5 needed. Right, 9 of them were the pool was 9 students and 11 faculty. Right, so this is our pool of students, or our pool to get from. Now, if you just look at part A, it wants to know what's the probability. I think A was all students. So A was what's the probability that you get all students. Now, is there a way we could tackle this without necessarily having to do any counting at all? Can anybody think of a way we could do that? Well, we could do a combination. We could do it with counting. I'm saying there is a way to do this without counting. So you say, what's the probability? What's the probability that you end up with? What's the probability of picking? Let's think about picking them one at a time, right? What's the probability of picking this student, right, as your first person? There's 9 students out of how many in your pool? Right? So you could think there's a 9 in 20 chance of getting that first student, right? And what happens after that? 8 in 20. I'm sorry. Then at that point, what happens though? 8 out of 19, right? Then there's only 7 students left out of 18, and then 6 out of 17, and finally there would only be 5 students to pick from out of the 16 remaining, right? So that's the probability of picking a student in each one. Now the thing is that, well, let's see, does order matter here? This is the probability of picking students, but then you also have to consider the fact that these could be different students in each section. So then you also have to say, okay, well that's this is the actual probability, but then how many ways could you pick 5? Right? Well, there's 9 students and we need 5 of them. Right? So the probability, we would have to take that probability but multiply it by all the different potential samples. So you could potentially work it out this way, where you would take this product. So if you multiply all those decimals out, you're going to get a small number, right? Then you'd have to also turn around and multiply it by this right here, whatever 9C5 is. So there's actually a better way to think about this, and we're going to see some problems like this. So, and as a fair warning, well, it's not really a warning. There's some tutors in the tutoring center who like to do these problems this way, but it's not the easiest way to do it. So I'm going to show you a better way. Okay, the better way to think about it is in general, the probability of an event, right? It's the number of ways that A can happen, right? Divided by the number of possibilities. Okay? So in this case, we think there's two things going on. There's students and there's faculty, right? So in total, how many ways can we pick 5 jurors? Well, we have 20 people to pick from, and we're going to pick 5 of them, right? So there's 20C5 ways to actually just pick 5 people for your jury, right, in general. This includes lots of different options where they could all be students or all be faculty or anywhere in between. This 20C5 is going to cover all of those possibilities. So this is going to cover all your possible 5-person juries out of the 20 total candidates. Now, what we want, though, is from the 9 students, we want to see all 5 of them. And from the 11 faculty, we want to see 0 of them. So this is how you're going to set these problems up. We're going to do another example like this in class today. But you say the number of ways that we can get all students on our jury is if of the 9 we get all 5, and from the 11 faculty we get 0. And the number of ways you can pick a jury total is 20C5. Right? This is going kind of back to the basic definition of probability. How many ways can it happen over how many possibilities? So if you try this out, what is 9C5? If you plug that in your calculator, something. 126. And what is 11C0? It should be 1. There's only one way to do it.
11.
Yeah. And then downstairs, what is 20C5?
15504.
What's that? 15504. Okay. And so then the answer is going to be 126 divided by 15504. And what's that going to get you? 0.00813. And some change. So 0.00. I don't know what it wants it rounded to. 812. It's probably going to want to round it to 4 decimal places. 0081 something. Oh no, it wants it 5. So 0.0081. It would round to 2, 3, 3. Yeah, let's check that. Yeah, okay. When we get to getting all, for part B, it's all faculty. So the setup is going to be pretty much the same. Okay. In this case, if we want the probability all faculty, right, then from the 9 students, we want none of them. And from the 11 faculty, we want all 5 of them. And downstairs still in total, there's 20C5 ways to pick our jurors. Yeah. So same format. You can get that. And then the other part C was probability of, at least mine, was 3 students, 2 faculty. 3 students, 2 faculty. Then we can do a similar. Okay, then that means from the 9 students, I want 3 of them. From the 11 faculty, I want 2 of them. And there's still 20C5 ways to pick my jury. So that would be the way you'd set up part C. So this is B, this is C. Okay. So anytime you're talking about picking a certain number of people from like two different groups, then you're going to use these combinations like this. All right. I think there's some other problems like that. We're going to do another one in class today too. But that's the general strategy. And notice that this 11 and 9 add up to 20, and this 3 and this 2 add up to 5. Right? It should always be the case that. And up here, 0 and 5 are 5, 11 and 9 is 20. So the totals. All right. So whatever those numbers come out to be, those should be the correct answers. Okay. I mean, yours might change though. Yours might be a different number of students and faculty because they have different iterations. But that's the general strategy. Okay? All right. Good question. We'll do another one today too. So we'll see another example. Anything else anybody wants to look at? For the homework? Yeah.
18.
Same section? Oh yeah, you had mentioned this one yesterday, right? And it was counting. 3 outfielders, 4 infielders, pitcher, catcher. Assume that outfielders and infielders are indistinguishable. How many batting orders are possible? Okay. So they're saying treat the infielders and outfielders as the same. Is that what they're saying? Then you have a pitcher and a catcher. Assuming that outfielders and infielders are indistinguishable, how many batting orders are possible? The number of batting orders possible. Okay. So, let's see. Ooh, that's a good one. Let me think about this. Number of batting orders possible. So we have 7. I think they're saying that there's 7 fielders, 1 pitcher, and 1 catcher. Is that what they're basically trying to propose? Is that right? And we're trying to figure out the number of orderings. Oh, I think I understand this problem. Did we? Oh, I bet I know what's going on here. Let me just look at their example real quick. Oh, do they not have it? Dude, what the heck? No example in my math lab? I know the problem. Here's the problem. Boom. So there may have been an example in the last one. Here's the idea. If you're looking at rearrangements, with repeats, okay, so like a classic example is if you're trying to like rearrange all the letters in the word, I don't know, what's the word that has repeating letters in it? Yeah, so Mississippi is like one of the classic examples. Right? So the idea is that you can swap all those letters around, but sometimes when you swap them around, you end up with the same thing because like you can swap out these S's and the letter still looks exactly the same. That's the idea. So in general, the way you would solve this is that, so how many letters are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So the number of rearrangements total, right, would be 11 factorial. But some of those are repeats, right? Some of those you have the same letters in the same place. And so what you do is you take that value and you divide out all the ways you can rearrange each letter. So like, for example, there's 1, 2, 3, 4 I's. So for those I's, every time you stick your letters in one place, you can rearrange the I's and you can switch out all the I's. So you would divide out a 4 factorial for the 4 I's. Okay. Then you see the S's happen 1, 2, 3, 4 times as well. So you would divide out another 4 factorial because of the 4 S's. and then the p's repeat twice, so you would divide out another 2 factorial because, right, p's repeat twice. So this is the strategy you take. Actually, I don't think we did an example like that in class. But it's so this would be your answer, whatever that comes out to be. Okay. All right. So I think what they're getting at here, right, with our batting average, is that there's 9 players, and if we were just looking at the rearrangements of the 9 players without treating any of them the same, we would think of 9 factorial ways, right? I think actually they were thinking of 3 infielders and four outfielders, or vice versa, whatever. It doesn't really matter how many are more ways, okay? So what? Yeah, go ahead.
Are you just multiplying the 4 factorial by?
Yeah, downstairs would be multiplied. Okay. So let me go back to the problem just to check. 3 outfielders, 4 infielders. Assume that the outfielders and infielders are indistinguishable. So treat all the outfielders the same, treat all the infielders the same. Assume they have like similar batting performances. Then what they're going for here is you'd say then, okay, this would be how many ways you could rearrange them before, but they're saying treat the infielders like repeats, like you can swap them out and it doesn't have much effect on the order. So then you need to divide out 3 factorial because of the outfielders, 4 factorial because of the infielders, and then, well, you don't need to divide these out because they're not repeats. So the pitcher and the catcher only pop up once. So I think the answer is going to be whatever 9 factorial over 3 factorial times 4 factorial is. So that would be, you could do it by hand. 9 factorial is 9 times 8 over 6 of them. Be whatever 9 times 8 times 7 times 5 is. What does it come out to be? Any takers on that? 9 times 8 times 7 times 5? What's that? 2520. 2520? Yeah. 2520. So that would be the different, I think that's what they're getting at there, is 2520. Yeah. Now, I didn't actually put any of those examples on the practice test, just so you know, those ones, but it does look like it popped. I thought I left those off the homework, but apparently I didn't. But that's how you solve them. You divide out the repeats. Okay. Any other questions about that?
Why did you just go to 5 on that?
Because I was assuming everybody else was just going to do it on their calculator, so I didn't actually write. It's because technically 9 factorial. There's a 4 factorial here, but that 4 factorial would just divide out with the bottom 4 factorial. Yeah, and 3 factorial is 6.
Gotcha. Okay.
So that's why I did that. Yeah. Mm-hmm. Good question. All right. Cool. Any other questions? No. Okay. Cool. So I will pull back up I'll pick up where we left off. We're getting close. So last time we talked, we were just leaving off with our counting strategies. So permutations, right? There was a few things going on here. First off, you have to consider whether replacement is allowed or not, right? Like, can I pick the same thing more than once? Once you decide that, if you can't pick the same thing more than once, what you see is this idea is that every time you pick something, you have less options for the next selection. And so if you're just looking at rearranging things, then we use permutations. So if you're picking up a certain number of things out of a total and you want to rearrange them, that's a permutation. But sometimes it doesn't actually matter what order you get picked in. So like if, in our example, I was just taking a sample. So it doesn't matter which student I pick first, second, or third, because I still have the same 3 students. Okay? And if the order doesn't matter, then that was when we would use the combination. And the formulas are similar. The combinations just divide out all those rearrangements is the idea. Okay? So,
Combination order doesn't matter.
correct, yeah. Combinations are appropriate when order doesn't matter. Yeah. So let's look at an example. So in a 5-card poker game, you get 5 cards from the deck of 52. How many unique 5-card hands are possible? Unique 5-card hands. So if I'm being dealt a card, is that with replacement or without replacement? Why? I agree. Yeah, so once I get a card, I can't throw it back in the deck and be dealt that card again, right? So it's without replacement. Does the order that you receive the cards matter, though? No, it doesn't, right? So we say this is, this is without replacement, and it looks like order is unimportant. Because it doesn't matter when you get the card, at the end of the day, you still have the same 5 cards. Okay? So if without replacement, order is unimportant, that means we're doing a combination. Okay? And what is our N? 52 cards. And how many are we going to get? 5. Yeah. Okay? So then it looks like the answer here is just going to be 52 cards combine 5. And you can plug that in your calculator. What do you get for that? 2.6 million. Yeah. What does anybody have it without Does yours just give you scientific notation?
I just did 52, choose 5.
Yeah. And was there anything between the 2 and the 6? Isn't there more?
No, it's 2,598,960.
Okay. 2. Just give me the numbers. 2.
5, 9, 9, 8, 9, 6,
6 0.
Yeah.
There you go. There you go. There's 2,598,960 possible hands you could be dealt if you're playing 5 cards. Okay? So check your calculator. You should be able to get that out of your combination button. 52C5. All right. Let's see here. I got a couple I want to. Sometimes we have to use our counting strategies to answer probability problems. So that's like I'm going to show you one in a second. Another interesting one too here is I do this. I started doing this a lot of quarters because this is sort of an interesting practice in what you think probabilities should be and what they actually are. So our section of Math 146 actually has a lot more than 30 students in it. How many people are in here today? Let's count.
30.
How many people are in here today?
40.
No, I mean, like, let's actually count.
30, 31, 29. 30, unless I can't.
I got more than that.
Wait, what?
Everybody? Okay, so everybody count.
Oh, I didn't count myself.
Count yourself.
There's 30.
Count yourself. How many students are there?
There's 30. I know, someone just popped up right now.
I got 31.
Ooh, we are.
Oh, wait, yeah, 31. Sometimes I only covered.
I thought I got 31, 2, 4, 6, 8, 12, 14, 16, 18, 20, 22, 24, 26, 27. No, now I'm getting 30.
I have 30.
Now I'm getting 30.
I got 30. Are you
I just got
counting? Hold on.
30 students.
37.
Except for, I think Steven here is around, but he left. Maybe he'll come back.
Oh, yeah.
He's going to screw up our experiment. Okay, anyways. So there's 30 students plus me. What do you think the probability that someone in here shares a birthday is? That you share a birthday with someone in this room?
No.
You think it's low?
Yeah.
Think it's uncommon?
Yes.
Okay. What do you think?
Can I just say something? I find it freaky that I have, in my department, I work with 3 other people that share my birthday.
Okay, so do you think it's likely or unlikely that you share a birthday with someone in this room?
Unlikely.
Okay. Does anybody think it's likely? Okay.
Well, maybe because she shares it with 3 people, and how many people work at your...
How many people work there?
25.
3 of you share a birthday?
That's just like 4
We'll see.
altogether, yeah.
So let's see. Let's figure out what the probability should be. What's the probability that at least 2 people share a birthday?
And these at least problems on the homework kept getting me all.
Okay, so this is one of those. This is a thing though, is that usually when there's an at least problem, the quickest way is to do it with the complement.
Okay.
Usually. Okay, he's back. So now we got 31 students. Okay. Okay, so there's 31 people here. I want to know what's the probability that at least 2 of us share a birthday. So if you define, let's say that A is at least 2 share, then what would be the complement of that?
29.
Yeah. No one shares, right?
Was it like 35 on the homework?
I don't know, but maybe. But a lot of times when you're talking about at least probabilities, it's actually quicker to do the complement probability and just subtract that from 1, right? So what I'm going to tackle is not this. I'm going to say I know that that's just going to be 1 minus the probability of the complement, and I'm going to go tackle this problem because it's actually a little easier to tackle that problem. Then I'll take that complement probability back later. Okay. So let's think about what is the probability that no one shares a birthday. Well, that's going to have to be the number of ways no one shares, right, divided by the number of ways that we could all have birthdays. Right? So we need to figure out how many ways can we actually could it happen that none of us share a birthday? And how many ways could we all just randomly have birthdays throughout the year? Okay. Anybody here born on February 29th of a leap year? Okay, so we don't have any like leap year anomalies. Okay, that's good. So that makes our job a little easier. So we can. So let's see. So I'll go down here. We need to figure this. The easier one is, okay, if we're just looking at how many ways, and I'm going to include myself here, how many ways can 32 people actually have birthdays? Just like unique birthdays. It's a lot of ways, right?
365.
Yeah, so you can have a birthday on 365 different ways. I can have a birthday on 365 days. Everyone in here has 365 different ways that their birthday could happen, right? So if you think about that, right? So you have we have 32 people, and we all have 365 ways that our birthdays could occur. Then the total number of ways it could happen is what? 365 to the 32. A lot of ways. That's a big number. I don't even care about it right now, but that's going to be our denominator. Okay? It's huge. All right? Now, let's think about what are the number of ways no one shares. Okay, so the first person, they could have a birthday on what, 365 days? They have 365 days, right? But the second person, if we can't share, what happens? 364. And the next person has less, right? In fact, all the way down to our 32nd. Each time we pick a new person, we have 1 day less to pick from out of the year. In fact, what we're really doing here is a permutation, right? We're saying how many ways can you pick 32 unique days out of a 365-day year and rearrange them. So what this number is actually going to be is 365 days permute 32. Because if we're forcing people to not share birthdays, then we can't pick with replacement. We have to pick our birthdays without replacement. Okay? So then the probability that no one shares a birthday is going to be the number of ways we could all have unique birthdays divided by the number of ways we can actually have birthdays. So what do you think? Anybody able to put this in their calculator and not have it yell at them?
Do you want to round it to
What's that?
2.429?
I was saying, can you put the whole thing in your calculator?
Oh,
This just as a whole quantity. I can do it like in Excel. So I can check. I'll do Excel just in case your calculators are yelling at you. So this would be the permutations of what? With 365 days, we're picking 32 of them, divided by 365 to the 32nd power. Excel tells me that's a 0.2467 chance. Anybody else able to get that?
That's what I got.
0.2467? Okay. Well then, what does that say about the probability that someone in here shares a birthday? That means that the probability that someone actually shares a birthday is 1 minus 0.2467, which is 0.7533. That tells us that there's a this is suggesting there's a 75% chance that someone in this room shares a birthday with someone else in this room. You believe it?
no.
You don't believe it? Okay, so let's try it. So we'll go around the room. Just tell us your birthday, like month and day, and then if they share your birthday, say that's my birthday. Okay, we'll start up here. We'll start up here. January 6th. March 14th. January 18th. November 12th. No, December 8th.
October 26th.
Okay.
August 4th.
August 4th.
July 7th.
July 7th.
August 7th.
February. We'll go that way. Yeah, it doesn't matter really. February 9th.
May 25th.
No, not yet.
September 27th.
May 4th.
January 14th.
February 7th. February 2nd.
What else?
October 24th.
November 6th. January 23rd.
Ooh, we're running out of options.
C.
Huh?
December 28th. May 21st.
September 10th.
Worked. September. Let's go. Let's see. We'll finish.
23rd.
See if anybody else shares. Yours was. Oh yeah, y'all have the same one, right? What was it that you shared?
September 10th.
September 10th. Okay.
May 7th.
May 7th.
January 1st.
October 14th. December 24th. March 2nd. October 5th. December 18th.
August 7th.
Oh, I'm December 3rd. So that's. Yeah. So we at least had one, right? So there you go. It wasn't lucky. Was it really lucky though? Because what was the odds of? What was the chances of it happening? I mean, there was a 75% chance it happened. Right? Look at what happens if you're in a room, like if you're in a room of, if you can just extend this out to a bigger population pretty easily. I don't know if I have any room, but I mean, just think about like if you are in somewhere that has say 40 people, right? The odds go up really fast because then you have 365 permute 40 over 365 to the 40th, right? For the odds of not sharing a birthday. So by the time you get up to 40 people, the odds of not sharing a birthday are going to go down a lot. So 365 permute 40 over 365 to the 40th, right? By then, there's only an 11% chance you don't share a birthday with someone. So by the time you're in a room with 40 people, there's a 90% chance that you share a birthday with someone in that room. Yeah. And if you go up to what, like 50? If you're in a room with 50 people or you work somewhere with 50 people, there's only a 3% chance that you don't share a birthday with someone. So, there you go. Interesting. And if you're in a room with 366 people, what's the probability you don't share a birthday with someone? Technically 367 people. What's the probability you don't share a birthday with anyone? Yeah.
Oh, 0.
0.
Yeah.
Right? If there's 360, or someone in there, not necessarily you, but someone in that room has to be sharing a birthday, right? If you have 367 people. Because there's only 366 days to pick from. Okay. All right. So, September 10th is our lucky day. I did this in my 107 class, and we had 3 people that shared a birthday. And there was only 25 people in that class. So, I've never done it and not had people share a birthday, so you guys were making me really nervous. I was getting nervous, yeah. I was starting to worry. I've never had it not work yet. One day it's not going to work though, right? Because that's just probability. One day it's not going to work. Yeah. Oh yeah. Oh, that's mine. Okay. So Easter egg hunt. Now, okay, this is going to be kind of like the one we just looked at on the homework. So Easter egg hunt has 100 eggs hidden out in wherever. And 4 of those eggs have $20 bills in them. So let's say that a kid finds 6 of those. What's the probability that one of those eggs has a $20 bill in it? Okay. This is probability that one egg of the 6 has $20. Right? So what we need to do, the basic definition of probability, says we need to figure out the number of ways you can have one egg of 6 with $20 divided by the number of ways you can just, find 6 eggs in general. Oops, that's fine. This is our task. Now, one of these numbers is a little easier to find, I think. Which one do you think that is? Yeah, normally the denominator is a little simpler. Okay. So if we're going to look at that one, so number of ways just to find 6 eggs. Okay. Well, how many eggs are out there? There's 100 of them out there, and how many am I going to find? 6. Can I find eggs with replacement? No, because I'm probably not throwing eggs back, right? At the end of the day, I have to have 6 in my basket, so I couldn't have thrown them back. So without replacement, doesn't matter what order you pick the eggs in. No, it doesn't. It doesn't matter if you pick this egg first, second, third, or fourth. It either has the $20 in it or it doesn't. So without replacement, order doesn't matter. This is a what? Combination. Order doesn't matter. Combination. Okay. So then we have 100 eggs. And we're going to find, this kid is going to find 6 of them. So this is the number of ways that could happen. So whatever 100C6 is, it's a big number. I'm not even going to write it down. But it's something. What is it? Did anybody actually calculate it?
11920524000.
Okay, so is that over a million or is that 11 million? Billion, hundreds of millions? I don't know. It's a lot of ways.
Yes, 1 billion.
1 billion. Ooh, wow. There's 1 billion ways to find those eggs. Shoot. Okay, so that's our denominator, but now we need to tackle the numerator. So how many ways can we get, say, 1 of the 6? The denominator? So the denominator is just, in general, how many ways could that kid have picked up 6 eggs? Well, there's 100 eggs out there. We want 6 of them. And the order doesn't matter. All right. So now we have to think about number of ways to get one of the 6 to have $20 in it. So what we're thinking about here is 1, 2, 3, 4, 5, 6 eggs, right? One of them has to have $20 in it. And these ones don't have $20 in them, right? So, how many ways can, say, the not $20 eggs be picked? By the way, how many have $20 in them? 4. And how many don't have? So then how many don't have? I'm talking about out in the field. If you go back to the problem, like out in the field, 4 have $20 bills in them. So that means that 96 don't, right? So if I'm going to end up with 5 eggs that don't have $20 in them, well, those 5 eggs are coming from a total of how many? 96. So the number of ways these can be picked is there's 96 eggs, and I want 5 of them, right? There's 96 eggs, and my kid has 5 of them. And there's 4 eggs here, and my kid found 1 of them. And boom, that's what you're going to do upstairs. So the answer is going to be 4C1. That's how many ways you can get 1 out of the 4 with 20. Times 9065, that's the number of ways you could pick 5 eggs out of 96 that don't have $20 bills in them. All right? So then our overall probability is going to be, this is our numerator, 4C1 times 96C5. And then downstairs, that's going to be that 100C6. And that's going to be our solution, whatever that comes out to be. What does that come out to be? For anybody who's able to put that in their calculator. Let's do 4 decimals. 205. 1. Yeah. All right. There you go. So actually, pretty good. There's a 20% chance that over a 20% chance that your kid might end up with one $20 bill in their Easter egg basket. It's pretty good. Okay. So this is like that one we saw with the jurors or whatever, the jury. So there's a total pool that you could pick from, but we want to see a certain number from 2 separate pools within that. So you set it up like this. All right. Okay. Let's see. I don't know if I had another example on here. I think that might have been all I had. Okay. Yes, I do. So the answer to that was 0.2051. All right. So we'll do a review day tomorrow. If you have questions you want to stick around and ask, we're a little early, so I can stick around if you want to ask those. But in the meantime, print out the practice test. Take a look at that tonight. Okay? Come tomorrow with questions. All right. And we will take a test on Thursday.